Hello everyone, welcome to a new session, and today we will study the heap data structure. So a heap data structure is a special type of complete binary tree that satisfies the heap property. So first of all, you should know that it is a binary tree, and it has a special property that is what makes it a heap property, and that is either it is a max heap or a min heap. It is a max heap when all the parents are greater than or equal to its children, and it is a min heap when the parent, all the parent is smaller than or equal to the children. For example, in this example, you see every parent node is greater than its children. For example, this parent node is greater than its children. This parent node is greater than its children. This parent node is greater than its children. So it is a max heap. And min heap is the other way. Every parent is smaller than its children or equal to its children. So another interesting fact that about the heap that you should know, that when it comes to actual programming, you store this in an array, not a tree. That is why when we visualize it in a tree, all levels are filled. You see, all levels are filled, and it is possible that last level is not completely filled, but there is always filled from left to right. So first of all, in this binary tree, when you go from top level to down levels, all levels are completely filled. Like, I mean, all the parents have its two children. And in the last level, it is possible that some parent node may not have all the children, but it always has its left children. It always starts from the left side. Let me show you some more examples. Heap data structure. So let's see some pictures here. See, all the pictures that you see, they are from top level. When you see this level and this level, so this level is not complete, but see, it is filled from the left side. For example, this part, it cannot leave this empty and have a right child, or this one, or this one, or this one. See, yeah, all of them. So let me show if there is some wrong example. Yeah, see, for example, this one. You cannot leave the left child empty. If that is left, that means it is not a complete binary tree. And the reason for that is because you represent that in an array. So if you look here, leaving a left child empty, that means leaving an empty space in the array, a blank space in the array, and that is not how array works. So for that reason, when you visualize your array in a binary tree, always all the levels are filled, and if the last level is not filled, at least it is starting it filling from the left side. So another thing, there are some mathematical relationship between all the nodes here. So when we said it is an array, how we can check, like how can we visualize it like a tree, and how do we know like the parent and children? So this mathematical relationship is established between all those nodes in heap data structure, or in this binary tree. For every node, the parent is I mean the index in the array, the index minus 1 divided by 2. The left child is 2i plus 1, right child is 2i plus 2. For example, let's check it with number 20. So number 20, the index of 20 in this array is 1, because you know that the array is 0-based index. So 0, 1. The index of 20 is 1. Now if you want to see its parent or its children, so the parent you get based on this formula. I, the index, minus 1. So the index was 1. 1 minus 1, 0. 0 divided by 2, 0. So that means the parent's index should be 0, 25, and that is the parent. See, the parent is 25, and in the array that the index is 0. The left child, 2i. So I is 1, 2i, 2 times 1, 2 plus 1, 3. So the left child is in the index 3. 0, 1, 2, 3. Number 9. See, 9 is the left child actually. And the right child is 2i plus 2. I is 1, so 2 times 1, 2, 2 plus 2, 4. So the right child is in the index 4. 0, 1, 2, 3, 4, 8. See, the right child is in the index 4, number 8. So these relationships are established between all those nodes in this array. That is how we can visualize in a binary tree. And there are some basic operations that you should know when you work with heap data structure. One of them is insertion, like you should know how to insert. And the key point that you should know that you always insert at the end, because it is an array, and when you add a new element, you just append that to the last part of, to the end of the array. When you insert it at the end, then you heapify that, because sometimes when you insert that at the end of the array, it may interrupt the heap property. For example, just an example, let's see if you insert here a number 40. Number 40. So, and when you put this number 40 in this binary tree, so you start from left side, so that means that should be a left child for the number 9. So the number 9 left child, number 40, see, it automatically destroy that property. Now 9 is not greater than 40. So you should know that when you first insert at the end and then heapify it, bubbling up. That means you should, when you insert here, then you check if it has the heap property or not. If not, then heapify that. Delete from the beginning, always from the root. And when you delete the root, replace this with the last element. And then check if it is heapified or not. If it is heapified, good. If not, then you heapify it downward. So now let's see how we can actually do them. For example, how we can insert them. So as I said, it is just an array. See here, we just created an array, named it heap, and now when you insert, simply you append the value at the end of the array. So append the new value at the end of this array. That means add the number 40 here, and when you represent that in this heap binary tree, so you insert that from the left side. Let's have it in the left side. Okay. Number 40. So now okay, it is much better. So now you see you have inserted number 40 here because you appended at the end of your array. So now when you look at this, it doesn't have the heap property anymore. Here this parent is not greater than its children. So you check if this happens, then you need to swap this here, and when 40 comes here and 9 come here, again it doesn't meet the heap property. Again you need to swap that. When 40 comes here, again you need to swap that until 40 comes here at the top, so that it has the heap property. So how we can do that? That's easy, as we can see in the picture. So first, when you insert the new element at the end of this array, so you get its index. So of course the index is the last one, and you can get that by the length minus 1. For example, 1, 2, 3, 4, 5, 6, 7, 8. If the length of this array is 8, the index of this last element is 7. So you say the heap size, the length of the heap, minus 1. So now you got the index. So, and you keep swapping this until this index is not in its right place. When it comes to its right place, then you stop that. However, it is always greater than 0. So you should not be like going until like until when you come here at the index 0, so you should stop that. For that reason, you always check if the index is greater than 0, and so you compare this one with its parent. So get the parent. How you get the parent of this? How you get the parent? Using this formula. So you have its index, and the index minus 1 divided by 2. So the index is 7. 7 minus 1, 6. 6 divided by 2, 3. So its parent is 3. 0, 1, 2, 3, number 9. So you got the parent. You get that like this here. So I already defined a method for parent just to write this mathematical formula in a separate function, so that it should not be very crowded here. Otherwise I could write directly that mathematical formula here, but I wrote that here. So you just pass the index here, and it calculates this, get the index of the parent, and brings it back to you. So when you have the index of the parent, you get that element. Now you got number 9 here, and you compare it with the new element in the heap. The index of this is the last one, 7, and that is number 40. So you say if index is greater than 0 and the parent is smaller than this new element, you need to swap them. And now the condition meets. The index is greater than 0 and the parent is less than this new node, so you need to swap that. So keep this parent index in a separate, in a temporary variable p called parent, for parent. So now we have the index of parent here, the index number 9, and swap the current one with its parent. The current node is number 40. Swap this with parent. It is a Python feature that when you swap, you can swap the then place. You don't need to define a temporary variable just to do the swap. So when you make the swap here, that means 40 comes here, 40 comes here, and 9 comes here. 9 comes here. This happens. So you need to update the index also. So now you should have this index, and previously it was the parent index. You had stored that here. Now it is the index of this new node. So you say the index equals to parent, which was this earlier. So now that you updated the index and you put 40 and 9 here, so 40 came here, you swap this to 40 came here, and 9 came here. So again, the index of 40, is it greater than 0? Yes, it is greater than 0. And get its parent. No, its parent is 20. So get its parent and see if it is less than this or not. So when you get the parent, you see it is less than the new node. So again, you swap it. You bring number 40 here, number 40 here, and number 20 here. you swapped 40 and 20. So you brought 40 here and 20 here, you swap these two. So see, now the index of the new element is 1. So is it greater than 0? Yes. And now you compare this with its parent. First get the parent, so you get the parent. And is the parent less than this new node? You see it is less than the new node. So again you swap them. You swap them, bring the number 40 here and 25 here. So 40 and 25. 40 here and 25 here. So now you see that you applied the heap property here. Now every parent node is greater than its children. So it is how you insert. Same operations with the deletion. When you delete a node, so you always delete from the root and replace the root with the last one. For example, here if you delete 40 and replace it with number 9, so you see that if it has the heap property, that is fine, you are lucky. But it doesn't have. So when you bring number 9 here, automatically you see that it is no longer greater than its children. So again you heapify this. This time you heapify down. Like when you inserted, you heapify upward, but when you delete, you heapify downward. Actually, even in some textbooks and some resources, they define this part in a separate function and call it heapify upward, and for the deletion they create a separate function and call it heapify downward. But I wrote that here in place. You can do it however you like, that's up to you. The point is that you should implement this concept. So same thing with deletion. Now you can implement that. In case you have any questions, you can ask your questions in the comment section, and I will check your questions and I will answer your questions. Until the next session, have a nice time.